Hello. Okay. Hi, dear students. Welcome to the class and good evening to everyone. So the people are almost they have joined. Fine. Coming to the in the last class, we have discussed about the production of the torque, rotating magnetic field, and also production of the torque and advantages of the star connected armature. No? Yes. Mainly in star connection, triplet harmonics eliminated in the lines, but they exist in the phases. Okay. Delta connection also, there is a circulating currents. No? That is the main drawback, circulating currents. Right? Rotating magnetic field, that is stator poles. The stator poles, they will rotate at synchronous speed. For the given time angle, the poles rotate equal space angle. Okay. Production of the torque. For the torque production, we have seen in generator, torque direction will be in opposite direction that of rotor rotation or primo rotation. But whereas in motor, the electromagnetic torque direction will be in the same direction of rotor rotation. Okay. So lambda is the angle between main field EMF, air gap EMF. Okay. Main field EMF and armature EMF. But whereas delta is the angle between stator field, rotor field and air gap field MMF. Yeah. But delta positive in the case of generator, delta is negative in the case of motor. And the expression for torque, electromagnetic torque, the expression for the torque is electromagnetic torque is equal to magnitude of electromagnetic torque. PEM, electromagnetic torque is equal to minus P by 2 mu naught pi RL by G into FM and FA sin lambda, where P is the number of poles. Where P is the number of poles. Okay. R is the radius of rotor core. L is the length of rotor core. G is the air gap length. FM is the main field EMF. That is stator EMF, rotor EMF. And FA, armature EMF. That is stator EMF. Lambda is the angle between FM and FA. This is called what? Torque angle. This is itself torque angle. Yeah. And a negative sign is there, na? Negative sign is because the two fields will try to align themselves. The two fields, stator field and rotor field, FM and FA, will try to align themselves. They will try to align themselves. So the rotor poles, stator poles, always they will try to align themselves. South pole of the stator always try to align the north pole of the rotor. So in that business, the torque will be continuous process takes place. Negative sign is because two fields will try to align. North pole and south pole will try to align themselves. Okay. So torque is depends upon what? Torque depends on the number of poles. It is depends upon radius of the rotor, length of the rotor dimensions. It is depends upon rotor dimensions. Power is proportional to volume of the rotor. Na? Volume of the rotor, torque also proportional to volume of the rotor, and it is inversely proportional to air gap length. Inversely, torque is inversely proportional to air gap length. When air gap length increases, flux decrease. Torque also decrease. And FM, rotor MMF and stator MMF, sine of the angle between both, sine lambda. Okay. Yeah. Now, and coming to on this topic, you can expect only 2 questions. Of course, whatever yesterday I have given conclusions, all the other questions. How you will give if rotor poles leads that act as a generator. You will give a diagram, and in that if rotor poles act, the machine act as a generator or motor. Rotor poles leads means generator. Rotor poles lags means motor. Yesterday conclusions are itself objective questions. See the 2 important questions they are. Listen. With the stationary armature rotating field. Stationary armature rotating field. Stationary armature, okay, rotating field. A rotating field. With this stationary armature, see this is a stator. The stator rotating field, fields are rotating, poles are rotating. With this rotating poles, okay. This is north pole and south pole, north pole and south pole. Rotor poles. Rotor poles are excited with DC, and stator poles. This is south pole, say. This is south pole of the stator, north pole of the rotor. North pole of the rotor. When both are rotating at synchronous speed, if stator pole is rotating at synchronous speed, when stator poles rotate at synchronous speed with respect to stator, NS say this is NS. And rotor also rotated synchronous speed. Rotor also rotated synchronous speed. Both will rotate in the same direction. Na? Both will rotate in the same direction. So, if a person is sitting on the stator, for example, say he is sitting on the stator, he is standing on the stator, say, right? He is a stator. His name is stator, say. Stator. Sitting on the stator. He is sitting on the stator. Person sitting on the stator. He is sitting on the stator. So south pole of the stator. Stator is not rotating. Na? What is the stator speed? Stator is 0 speed. But with respect to stator poles are rotating at what speed? Synchronous speed. Armature field, and also air gap field also you can say. Air gap field means resultant field. It will rotate at synchronous speed with respect to stator. Stator is at 0 speed, na? Stator is not rotating. Stator is stationary, stator poles are rotating. Therefore, conclusion is the armature field are poles or MMF, and air gap MMF. Air gap field, it will rotate at synchronous speed. Will rotate at synchronous speed with respect to stator. Correct? With respect to stator. Stator is at 0 speed. Stator Stator is at zero speed, but poles rotate at synchronous speed. Na? So what is the relative speed? Ns. And the armature field with respect to rotor, at what speed they will rotate? Armature field with respect to rotor. Armature field is rotating at synchronous speed, rotor also rotating at synchronous speed. What is the relative motion? Zero. So two fields are rotating at synchronous speed. Then I can say relative speed between stator poles and rotor poles, zero. Rotor is zero, stator is zero. Stator poles rotating at synchronous speed, rotor also rotating. Therefore, the conclusion is the armature field. The armature field are poles and air gap field. Air gap field means resultant of both. Resultant. Phi M and phi R. When both are rotating, where armature poles are there, resultant flux also there. The armature field and air gap field. The armature field and air gap field is stationary. Is stationary with respect to rotor. Stationary with respect to rotor. Because poles rotate at synchronous speeds, poles rotate at ns, and rotor also rotate at ns. Rotor also rotate at ns. Therefore, relative speed is zero. Relative speed is zero. Relative speed is zero means both are stationary. And in which direction armature poles rotate? Armature poles rotate in the same direction of rotor rotation. Rotor rotating clockwise, say armature poles also must rotate in clockwise direction. Therefore, the armature field are poles and air gap field. Air gap field will rotate in the same direction of rotor rotation. Okay. These are itself very important conclusions. Just to go through that, all these are important conclusions. When I don't want to give the question answers, all answers I am giving. You can find in the material on this topic. I have given questions. MSQs, multiple select answer. Okay. On this topic, I have given topic wise. I am giving answers directly and read the questions, answer you can find. Okay. I hope this is clear now. Yes. Dear students, once again, see to me. This is stator. Stator is stationary. Stop writing, listen. Stator is stationary, no? Yes. See here. Stator is stationary. But stator poles rotating at synchronous speed. This is the stator. It is stationary. Stator poles rotating at synchronous speed. And rotor. Anyhow, rotor is rotating at synchronous speed. But armature poles with respect to rotor, zero speed. Relative speed zero. Armature poles rotate in the same direction of rotor rotation. Whether rotate clockwise, if rotor rotate counterclockwise, poles also rotate counterclockwise. But with respect to stator poles rotating at synchronous speed. Because stator is zero speed, stator poles are ns. What is the relative speed? Ns minus 0 is equal to ns. Next concept is based on, this is stationary armature, na? Yes. Now next, rotating armature, let me take. Rotating armature and stationary field. Rotating armature and stationary field. Rotating armature, stationary field. For this, Yeah. Poles are fixed to the stator. These are the poles, say, salient poles fixed to the stator. They are excited with DC. Of course, they are excited with DC current, and this is the rotor, say. This is the rotor, rotating armature. The rotor. On this, we will keep the armature winding, na? Yes. On this, we will keep armature winding. Field winding also, of course. Field winding, we will keep the field winding. On this, we will keep the field winding. Based on the field. Okay. They are excited with the DC. Based on that, it acts as a north pole, it acts as a south pole, say. They are excited with the DC current. DC. That is there, okay, fine. Leave it. Now, mainly, I want to focus on the rotor, armature poles. Armature poles. Okay, armature poles. So now let me delete all these things, because mainly I want to highlight. Okay. I'm not writing DC excitation. You can understand that. Fine. Right. But rotor, on the rotor, what we are doing? On the rotor, field winding can be kept. Okay. This is north pole. Say, for example, this is the north pole. This is the north pole. And this is the south pole. South pole. Fine. And on the rotor, we are keeping winding. R, R dash U, Y, Y dash U, B, B dash. Three-phase winding we will keep. On the rotor, we will keep the three-phase winding. Armature winding. Armature winding is kept on the rotor. Armature is rotating. Poles are fixed to the stator. Okay. Yeah. I have shown at the time of construction rotating armature and stationary field. And here the conclusions are, see, very important. Whatever I am writing, each statement is one objective question. Instead of giving question answer, every point is itself important. See, when main field poles means what? The poles which are fixed to the stator. So main field poles are stationary with respect to stator. Correct? This is the stator. Okay, and this is rotor. Main field poles are stationary with respect to stator. Because stator is stationary. Stator is at what speed? Zero speed. Na? 0 RPM. It is not rotating. 0 RPM. The pole also 0 RPM. Pole also at 0 RPM. Na? Yes, it is also 0 RPM. It is also not rotating. Then both are stationary with respect to each other. The main field poles are here. Important thing is main field MMF. Main field under DC. Main field poles are MMF. Main field MMF is stationary with respect to stator. Is stationary with respect to stator. Okay. Main field MMF. Sorry. Main field MMF. Main field MMF or main field poles. Main field poles or MMF is stationary with respect to stator. With respect to stator. Correct? Yes. So poles are fixed to the stator. Stator is not rotating, poles are not rotating. Both are stationary. Na? Yes. Relative speed 0. That is said to be stationary. And when main field poles are stationary, armature poles also will form here. Armature pole, the pole will form here. For example, say this is the south pole is formed on the rotor. South pole is formed on the rotor. Because on the north pole, south pole, with some angle will be there. Forget about it. Some angle will be there. Leave it. That is torque angle will be there. Na? Leave it. Yeah. This is south pole. Under north pole, definitely south pole must be exist. Na? Yes, with some angle, leave that angle. So once these main field poles are stationary with respect to stator, this armature poles also must be stationary. Correct? Yes. So main field poles are fixed to the stator, they are stationary. Then armature poles also must be stationary. These poles are already fixed with respect to stator. Correct? Yes. These poles are stationary with respect to stator. These are fixed to the stator. And these are rotor poles. Okay. Once these are stationary, other armature poles also must be stationary with respect to stator. Because these two are stationary. Try to understand. If a person is sitting on the stator, say a person is sitting on the stator. Under him, north pole always there. And armature pole also, south pole must be there. Because main field poles and armature poles both are stationary with respect to each other. Both are stationary with respect to each other. Compulsory. Both must be, two fields must be stationary. So therefore, I mean to say, main field poles are stationary with respect to stator. Therefore, the armature field or poles also must be stationary. Must be stationary with respect to stator. Must be stationary with respect to stator. Because the two fields, that is main field and armature field. Main field and armature field. Armature field must be stationary with respect to each other. The two fields must be stationary. For the production of unidirectional torque, two fields must be stationary. Must be stationary with respect to each other. Must be stationary with respect to each other. Okay. So main armature poles also stationary with respect to stator. Then in which direction armature has to be rotated? Which direction armature poles must rotate? See. Can you tell me? When rotor rotating clockwise direction, say. Rotor is rotating in clockwise direction. This rotor is rotating in clockwise. Now, which direction poles should rotate? Tell me. Which direction poles must rotate? Armature poles. Armature poles. And the rotor poles, armature poles. Which direction they have to rotate? Same direction or opposite direction? Which direction? Some people are saying clockwise or counterclockwise. If rotor is rotating clockwise, means armature poles must rotate in counterclockwise direction, opposite direction. It's a rotor rotation, say. I am taking if it is a rotor rotation. If rotor rotation is in clockwise direction, this is rotor rotation. Say this is what? Rotor rotation. Rotor rotation is in clockwise direction. Poles must rotate in counterclockwise direction. Rotor rotation. This is a rotor rotation. Rotor rotation. Rotor is rotating in clockwise direction. But when rotor rotation is in clockwise, direction, poles must rotate in anti-clockwise direction. If it is rotor is clockwise, but poles must rotate in counterclockwise direction. Okay. This is a rotor rotation. Poles must rotate opposite direction. Right? Yeah. Why? Because the main field poles are stationary. When rotor rotate, pole must rotate in opposite direction. Pole must rotate opposite direction. Then only the south pole will comes under the north pole. South pole will comes under the north pole. Okay. So armature poles must be stationary. When rotor rotate, armature rotate, but on the armature, poles will rotate in counterclockwise direction. The RMF will produce. On the armature, RMF is produced. If you rotate rotor clockwise, armature poles will rotate in counterclockwise direction. So the statement is C. The armature field the armature field or poles will rotate in opposite direction. In opposite direction that of rotor rotation. Opposite direction that of rotor rotation. Opposite direction that of rotor rotation. These are the conclusions. Opposite direction. Right? Opposite direction. Clear? Yes. For example, listen to me. This is the rotor, say, dear students. See here, this is the rotor. See, this is the rotor. Okay. Stator is poles is here. You have to understand this north pole is there here. Okay. Can you understand? This is a rotor, but north pole is here. See to me. North pole is here. But here which pole is forming? South pole is forming. South pole is forming, na? Yes. South pole is forming. On that north pole must be there. Both must be one under other. Okay. Yes. But when rotor is rotating in clockwise, when rotor rotate clockwise, this pole must rotate in opposite direction. Pole must rotate in opposite direction. Then only it has to come to under north pole. And when rotor rotate, again this pole has to rotate in counterclockwise direction, opposite direction. It must rotate in opposite direction. And when rotor rotate, pole also must be rotated in opposite direction. Opposite direction. Right? Okay? If rotor rotate at right? Yes. If rotor rotate 180 degrees, say, if rotor rotate 180 degrees, pole rotate also 180 degrees. If rotor rotate 30 degrees, pole rotate 30 degrees opposite. Pole rotate 30 degrees. And like this, if rotor is rotated 180 degrees, say, from here onwards, na, yes, it is rotated 180 degrees, pole also rotated 180 degrees. Opposite direction. There only two fields must be stationary. Okay. Yeah. Fine. So these are the statements. Any doubt in this, please ask. Any doubt in this question? No. Just let me clarify 1 or 2 minutes and then we will go to the next topic. Yeah. Okay. Tell me. Hello.
Hello.
Hello. Tell me.
Good evening. Sir, in the previous case, I am not understand the how that air gap MMF will be.
Air gap is resultant of both. The north pole, south pole is rotating, na? Phi m, phi r is equal to phi m and phi a. Resultant. Resultant also will be in between that.
Okay, means both are in the same direction, so this will be resultant.
Resultant also same direction. Okay. Resultant also same direction. When these are rotating, that also must be in between. Resultant of both. That will also rotate in same direction.
Okay.
Okay. Yes. Yeah. Sirisha, any doubt? I hope already you are completed induction motors. This kind of questions, so many questions will be there actually in induction motors. Over.
Sir, right. Where is this configuration used?
This configuration can be used very small machines. I have given one topic, advantages of stationary armature. This is rotating armature, na? Yes.
Yes, sir.
Generally, alternators are stationary. Rotating armatures are very small. In your laboratory, you can use very small rating. You can use. This cost is less, strictly speaking. All educational institute, you go and see in your college, you can find it is rotate armature. If you find 4 slip rings are there, say rotating armature.
So, sir, in generating station, it is fixed armature.
Yes, definitely. Unless otherwise mentioned, also it is alternatives of stationary armature only you need to take. This is okay, very sir. Rare. This is very rare.
Small and sir, field is stationary in both the cases.
No. This here field means main field. Say main field means DC excitation poles. Poles are excited with DC. I am not showing on this. Actually, field current will be there, na? These poles are stationary. Earlier poles, what happened? These poles are rotating or not?
Yes, sir.
They rotate, but these salient poles only fixed to the stator. Winding earlier we kept here on this. Earlier we have kept the winding on the stator, armature. But now we are keeping the winding on the rotor.
Yes, sir.
So that is the thing. When these poles are fixed, when rotor rotate, poles must rotate anti-clockwise because the south pole has to come under the north pole. Dear student, you have to think only in the direction. Two fields must be stationary with respect to each other. That is a concept. So once this pole is fixed and south pole must be under that. So when rotor rotate, then pole will rotate equal speed in opposite direction. Then only it will come to here. Correct? Then only the south pole earlier here, when rotor rotates, south pole has to rotate in this direction such that the south pole must be always under the north pole.
Yes, sir. So in both the cases, magnetic locking should be maintained at all times.
Yeah, exactly. That's the reason two fields must be stationary.
That means in an induction machine, means both starter and rotor field are rotating. So this is more confusing. Na?
Where?
In the induction machines.
Oh, yeah. That is also two fields must be stationary only, but both rotating fine. When rotor rotate, on the rotor field again rotate at slip speed.
Yes.
That is okay. Yeah, I don't want to bother about those things because this topic is I want to make very clear. Okay, these are the standard questions, direct questions. If questions are coming, means these are only the statements. You see any examination, these are only the statements. Okay. Yeah. Now let us go to the next topic. Sirisha. Hello. Sirisha. Okay. Let us go to the next topic. We will come to the doubts later. The next topic is armature reaction. Armature reaction. Armature reaction. Armature reaction, the effect of armature flux on main field flux. The effect of armature flux phi A on main field flux. On main field flux phi M is called armature reaction. Is called armature reaction. The effect of armature flux on main field flux is called armature reaction. See, the two fluxes are crosses the air gap. Na? Armature flux crosses and main field flux also crosses. Both are stationary with respect to each other. Both are stationary with respect to each other. So therefore, the two fluxes are maybe aiding, both are crossing air gap. Na? Yes. So, on the stator, north pole to south pole, and rotor also north pole to south pole. And both are crossing air gap. If both may be aiding, both may be opposing. If both are aiding, say, armature flux and main flux, both are aiding, that is said to be magnetization. If two fluxes are opposing, say, demagnetization. Perpendicular, say, cross magnetization. But it is magnetization or demagnetization, it depends on the power factor of the load. Power factor of the load. Armature reaction depends on the magnitude of the load. These things, again, we are going to see. Armature reaction. Armature reaction depends on the power factor of the load. Magnitude of the load and load power factor depends on the magnitude of the load. Magnitude of the load and load power factor. Load power factor. Load and load power factor. Now let us see for various power factors. The power factors are there now. Load power factors. Lagging power factor, leading power factor, UPF, and also partial load, RL load, 0.8 lagging, 0.6 lagging, 0.8 leading. How armature reaction depends. Definitely it depends on the magnitude of the load, no doubt. When load increases, armature current increases, armature flux also increases. When armature flux increases, armature reaction also increases. So let us see how it is depends on the power factor of the load. Power factor of the load. Yeah. First, let me take with UPF. First one, UPF for unity power factor. For unity power factor, I will explain first with phasor diagrams, and after that I will show with physical diagram how exactly magnetization, demagnetization I am going to explain. First, let me show with easy understanding purpose with phasor diagram. This is UPF, and when this is main field flux. See, this is main field flux. The main field flux. This is induced EMF E. Induced EMF E. Flux is always along the direct axis. Induced EMF is along the Q axis. Induced EMF is always along the quadrature axis. Okay. Quadrature axis. E always on the quadrature axis. Because E lags flux by 90 degrees. Na? When phasors are rotating in counterclockwise direction, E lags the flux by 90 degrees. That already we concluded. Flux along the D axis, induced EMF is going to be quadrature axis. Now, for unity power factor means current also in same phase. Current will be in phase with voltage. Current is in phase with voltage. Flux also in phase with voltage. Armature flux also in phase with voltage. Armature flux also in phase. And how these two fluxes? See, this is the main field flux. This is the main field flux. Armature flux is exactly perpendicular. Armature flux is perpendicular. The perpendicular means it distorts the air gap flux. Distorted air gap flux. The distortion is called cross magnetization. Cross magnetization. Since the phi A is in quadrature with phi M. Phi A is in quadrature. Quadrature to perpendicular. Is in quadrature with phi M. Therefore, it distort the air gap flux. Distort the air gap flux. Air gap flux. And distortion is said to be, armature reaction is said to be purely cross magnetization. Purely cross magnetization. Perpendicular, when it is perpendicular, it is cross magnetization. Distort flux lines. Distort. Cross magnetization. Now let us take for another power factor, ZPF lagging, say. For ZPF lagging. Second one is for ZPF lagging, zero power factor lagging. That is pure inductive load. Pure inductive load. Earlier pure capacitive resistive load, na? UPF means pure resistive load it is. Pure resistive load. This is pure inductive load. And for ZPF lagging, okay. For ZPF lagging, this is phi M. Main field flux along the direct axis is always fixed. This is phi M, main field flux. This is induced EMF. These two are fixed. But for ZPF lagging means current IA lags. IA lags 90 degrees. Lagging the E. When current lags means flux also lags. Phi also lags. Therefore, how both are? Main field flux is in this direction. Phi M is in this direction, but phi A opposite direction. This is phi A opposite direction. So phi A opposes the phi M. Therefore, phi A opposes the phi M. Opposes the phi M. Then what is the net flux? Phi R. Phi R is equal to phi M minus phi A. Air gap flux and resultant flux. Phi M minus phi A. That net flux will decrease. When net flux decrease, generated MF also decrease, terminal voltage also will decrease. When net flux is decreasing, generated MF, terminal voltage decrease. Then this is said to be purely demagnetization. Said to be purely demagnetization. Armature reaction is said to be, since net flux is decreased, since net flux is decreased. So once net flux is decreased means armature reaction is said to be, therefore armature reaction is said to be purely demagnetization. Flux is reduced means purely demagnetization. Armature reaction is purely demagnetization. Okay. Listen. When net flux is decreased, E decreasing, yes, E decreasing. I want 400 volts, say. I want exactly 400 volts. But as load increases, inductive load, voltage less than 400. Voltage less than 400. It is coming some 380 volts, say 380 volts. But still I want to maintain 400. I have to increase the voltage. What to do? Field current has to be increased. We need to increase the field current. Okay. Alternator supplying for lagging power factor loads. Lagging power factor loads, due to demagnetization, net flux decreases, EMF decreases. So alternator supplying for lagging power factor loads, voltage drop takes place. In voltage drop, how it is compensated? By increasing the field current. If you increase the field current, again voltage will be increased. So conclusion is, an alternator supplying for lagging power factor loads are generally overexcited. Overexcited means more field current is required to maintain the rated terminal voltage. If you want to maintain rated terminal voltage, as load increases, right, voltage decreases, but to compensate the voltage drop, field current has to be increased. More field current, overexcited. So the statement is, an alternator supplying for lagging power factor loads. An alternator supplying for lagging power factor loads are generally overexcited. And that is more field current is required. More field current is required. More field current is required to maintain the rated terminal voltage. To maintain rated terminal voltage. Rated terminal voltage. To maintain the rated terminal voltage, current has to be increased, more current. Same conclusion for capacitor loads, what we are going to see. For capacitor load, underexcited. Because capacitor load magnetization voltage increases. But to maintain the same thing, you need to decrease the excitation. So now let us see for, this is for ZPF lagging. Okay. For ZPF leading, see for ZPF leading. For ZPF leading, third one, ZPF leading. For pure capacitive loads, for pure capacitive loads, there right. This is phi m, E. ZPF leading. ZPF leading means current in this direction. This is IA. So this is phi A. IA and phi A. Now, two fluxes are aiding. Two fluxes are main field flux. Say, if this is the main field flux phi M, armature flux also in the same direction. Both are in same phase. Both are aiding. Phasors are rotating. Current IA leads the E. Therefore, armature reaction. Armature flux aiding phi A is in phase. Phi A is in phase with phi M. That is, phi A is aiding. Phi A is aiding with phi M. Aiding with phi M. Therefore, what is net flux? Resultant flux phi R. Phi R is equal to phi M plus phi A. So net flux will increase. When net flux increase, generated EMF increase, terminal voltage also increase. Terminal voltage also increase. And when net flux increasing means it is said to be armature reaction is said to be purely magnetization. Purely magnetization. Why? Because net flux is increasing. Na? When net flux is increasing, it is said to be purely magnetization. Similarly, when alternator connected with the load, as load increases, armature flux, main field flux, both are increasing, net flux increasing, net voltage increasing. No load condition 400 volts say. But when load corrected, it is more than 400. Voltage is 450, increase, voltage rise. But to maintain the same thing, what to do? Field current has to be reduced. The main field flux you have to reduce. When the armature flux is aiding, net flux increases, then you decrease the phi M. Field current has to be decreased to maintain the rated voltage. Alternator is said to be under excited. Less field current is required. To maintain the rated voltage. మీకు ఎగ్జామినేషన్ లో ఎలా అడుగుతారంటే in the case of examination alternator, right? So and so a 300 kVA alternator supplying to the load, supplying to the 0.8 lagging power factor or ZPF lagging, ZPF leading. So in which case field current is less? Field current is less for capacitive loads. So therefore, an alternator supplying for leading power factor loads. Generally loads are generally under excited. That is less field current is required. Less field current is required to maintain the rated terminal voltage. Rated terminal voltage. Field current is less field current is required. This is for ZPF leading. Next, so far we have taken pure resistive load, pure inductive load, pure capacitive load. Now partial load, like RL load, 0.8 lagging load, RC load, 0.8 leading load. Okay. The fourth case, 0.8 power factor, 0.8 lagging power factor. 0.8 lagging power factor. That is what type of load they are? RL load. Resistive plus inductive load. For this, if you take this is flux phi m. Flux phi m is E, induced EMF E. Now for inductive load, how it is? This is IA. IA lagging. Say this is the power factor angle. The power factor angle phi, angle between E and IA. Say. Actually, we are going to call it psi power factor angle, internal power factor angle antam. Angle between E and IA, it is said to be internal power factor angle. So with respect to that, we are seeing power factor angle. Okay, phasors are lagging, na? IA lags. When IA lags means flux also in the same direction. Phi A also same. Phi A also same. But that phi A can be divided into two components. That phi A can be divided into two components. This is said to be phi AD demagnetizing component, and this is phi AC cross magnetizing component. So two components are there. Phi AD is the demagnetizing component. Demagnetizing component of phi A. And phi AC is the cross magnetizing component. Cross magnetizing component of phi A. So two components are there. Both demagnetization component, cross magnetizing component. Then what is the armature reaction? Therefore, armature reaction is partly demagnetization, not purely. Purely means earlier cases only magnetization, or only demagnetization, or only cross magnetization. That is pure, only one component. But here two components are there now. I am dividing this flux into two components, two perpendicular components, one along the direct axis, another along the quadrature axis. So phi AD causing demagnetization, phi AC causing cross magnetization. Therefore, it is not purely. Both are there means partly. It is partly demagnetization plus partly cross magnetization. Partly demagnetization, partly cross magnetization. This is for 0.8 lagging power factor. Now, for 0.8 leading power factor. For 0.8 leading power factor, they are said to be resistive and capacitive loads. Resistive and capacitive loads. For resistive and capacitive load, this is phi m, E, and IA. This is IA. Leading, na? Current leads the voltage. Leading power factor means current is leading the voltage. When IA, flux will be always in same phase. Are you getting? Flux will be always in phase. Proportional in phase. And that phi A can be again divided into two components. Phi A can be divided into two components. So this is in phase. In phase component causes what? Magnetization. Phi A magnetization, and this is phi AC, cross magnetization. So phi AM is the magnetizing component of phi A. Component. Magnetizing component of phi A. Magnetizing component of phi A. Whereas phi AC is the cross magnetizing component. Cross magnetizing component of phi A. Cross magnetizing component of phi A. Therefore, what is both are there means partly magnetization, partly cross magnetization. So armature reaction is said to be partly magnetization plus partly cross magnetization. Partly cross magnetization. Okay? Yeah. So this is armature reaction in the case of generator, alternator, whatever we have seen, generator. For lagging power factor demagnetization, leading power factor magnetization. Whereas armature reaction for motor, say, for motor it is quite opposite. For motor it is going to be quite opposite. Why? Why? Because generator is delivering the current, but motor is taking the current. Generator is giving the current, motor is receiving the current. So same power factor, currents are exactly opposite direction. Exactly opposite. When current is opposite means armature reaction also opposite. Let me compare. I don't want to draw for all phasors. I will draw for one phasor. 0.8 lagging phasor. I will take both generator and also motor. So that I would like to show armature reaction in two cases are quite opposite. After that, I am going to give the table directly, straight away. You know generator well, motor apply exactly opposite. Okay. See, synchronous motor. Whatever we have seen for generator, na? Yes. Let me compare. This is phi m anyhow. This is phi m. Main field flux. Phi m. Main field flux. And this is E. E. That E is same. Generator also, motor also same. For generator it is EG. Motor it is EB. Motor it is back EMF EB. Red color I am writing na EB. But EG also quadrature axis, EB also same. Induced EMF. Generator motor induced EMF equation also same. That is induced EMF. Generator we will call generator EMF, motor we will call back EMF. Both are same. EB. For generator, this is IA, na? Yes. For lagging power factor, I am drawing. This is IA. IA for generator. Generator means alternator, IA in this direction. But motor, IA will be exactly opposite direction. This is for motor. Motor current is exactly opposite direction. Motor current is exactly opposite direction. Phi A. This is IA. What for? For motor. This is for motor. Exactly opposite direction. For same power factor, 0.8 lagging only. Why? I have told generator giving, motor taking. Not only that. Technically speaking, see, in generator, E and V both will be in same direction. Generator EMF and V both will be in same direction, but some angle will be there. That angle we are going to call delta. Delta. But delta some 30 degrees say. 30 degrees also both are in same direction. Yes, both are in same direction. Generator EMF, V. In generator, both are the same. Whereas for motor, how the current, how the terminal voltage, it will be V, back EMF. This is V for motor. V for motor. Okay, this is V for generator. Generator is same. Generator in the same direction. Motor, EB. EB and EG both are in the same direction, but V will be opposite direction. V will be opposite direction. And strictly speaking, power factor is the angle between V and IA. Power factor is the angle between phi is the angle between V and IA. That is a power factor angle. Power factor angle. So that is phi, and this is phi, na? This is also phi. These vectors are rotating counterclockwise, and these vectors are rotating counterclockwise. You observe for generator and motor, this current lags this voltage. Lagging power factor, lagging, na? Yes. And here also this current lags the voltage with some angle. Lagging power factor. Both are lagging. So two cases for lagging power factor, armature current is exactly in opposite direction. And when armature current is opposite direction, Flux will be in same phase with the armature flux. This is phi A and this is phi A. This is phi A for motor phi A. Phi A. Now divide that into two components. For this, if you divide that into two components, how it is going to be? These are the two components. Phi A can be divided into two components. What is this component? Phi AD. Phi AD for generator. This is phi AC. Phi AC. Whereas for motor, this is one component and this is another component. What it is causing phi A? M. Phi AM. This is phi AC. Phi AC. Phi AC. Okay. The phasor is both for lagging power factor only, generator and motor. Machine is acting as generator and motor for 0.8 lagging power factor say. So for 0.8 lagging power factor, what is armature reaction in the case of generator? Partly demagnetization, partly cross magnetization. Both are there. Partly demagnetization, partly cross magnetization. Whereas for motor, you see, it is partly magnetization, partly cross magnetization. Magnetization, cross magnetization. So this phasor diagram is phasor diagram. These things. Phasor diagram. For 0.8 lagging power factor. Phasor diagram. Both for generator and motor. For lagging power factor. For 0.8 lagging power factor. I am writing for 0.8 lagging power factor. Okay. Then what is the armature reaction? Armature reaction for generator. Armature reaction for generator, partly demagnetization plus partly cross magnetization. Whereas for motor, armature reaction in the case of motor. In motor, this is generator, no? Yes, this is a generator. For generator. For motor, what is armature reaction? For motor, armature reaction is partly magnetization plus partly cross magnetization. Partly magnetization, partly cross magnetization. Okay. So then everywhere I have shown only lagging power factor, and everywhere just you change the current direction, current phasor, then armature reaction quite opposite. Okay. So for ZPF lagging, say ZPF lagging alternator purely demagnetization, but motor it will be purely magnetization. Okay. When current is in this direction, but motor current opposite direction. Quite opposite. So let me give the table instead of drawing the many diagram, not required. No? Yes, you are going to write competitive examination. Conclusions must be. Let me give the table. For generator and motor. Okay. Yeah. See, this is for power factor. This is a power factor. Alternator or generator. This is alternator. Generator. synchronous motor. Synchronous motor. For various power factors, let us see. For various power factor, UPF. For unity power factor, what is armature reaction? Armature reaction is alternator, purely cross magnetization. Purely cross magnetization. Purely cross magnetization. Motor also purely cross magnetization. Quadrature. One is upwards, one may be downwards. Both are perpendicular. Both are perpendicular. Here also purely cross magnetization. Purely cross magnetization. Purely cross magnetization. And ZPF lagging. ZPF lagging. UPF, this is ZPF lagging. ZPF lagging, it is purely demagnetization. Demagnetization. But whereas here purely magnetization. For synchronous motor, purely magnetization, ZPF lagging. And ZPF leading. ZPF leading, it is purely magnetization in the case of generator, but motor it is purely demagnetization. Demagnetization. ZPF leading. Now 0.8 lagging power factor. For 0.8 lagging power factor, 0.8 lagging power factor, it is partly demagnetization plus partly cross magnetization. Cross magnetization. Here partly magnetization plus partly cross magnetization. Cross magnetization. Similarly, for 0.8 leading power factor, for 0.8 leading power factor, it will be partly magnetization leading power factor plus partly demagnetization. No, cross magnetization. Here partly demagnetization plus partly cross magnetization. Okay. For UPF, partly cross magnetization, demagnetization, ZPF lagging. This is for ZPF leading. These are very, very common questions, but at the same time, very important also, very simple also. Everybody can able to do these questions, this type of questions, correct? Taken? Yes. So you know generator very well. For motor, just apply opposite. Opposite. Questions are very direct questions. Very direct, straightforward questions. Only thing is you have to read the question in full. Armature reaction for 0.8 lagging power factor. Is it generator or motor? You have to wait. Then only you have to go answer. Because options will be same now. Options only 4 options. Magnetization, demagnetization, cross magnetization. Okay. These are only the cases now. Yes. So all options, they will be valid both for generator and motor, but options are given. Is it for generator and motor? You need to see. Okay. Indirect questions. how the indirect questions will be given. Direct questions I don't want to discuss. You can, nothing is there. Indirect questions. Let me give. I will give previous GATE examination question. So taken. Take down. The question is a synchronous motor. A synchronous motor is operating on the bus bar. A synchronous motor is operating on the bus bar. Operating on the bus bar at no load condition. At no load condition. At no load condition. Okay, yes. The air gap flux was found to be, the air gap flux was found to be 25 milliwebers. Air gap flux entered both phi m and phi a. The air gap flux was found to be 25 milliwebers. 25 milliwebers. Now, if the armature flux is when the armature is disconnected, when the armature is disconnected, when the armature is disconnected from the supply, by keeping field excitation same, by keeping field excitation same. By keeping field excitation same, then the air gap flux was found to be, then the air gap flux was found to be 20 milliwebers. 20 milliwebers. 20 milliwebers. Then the no load power factor, then the no load power factor of synchronous motor would be, no load power factor of synchronous motor would be A bit, lagging B bit, leading C bit, UPF D bit, none. Think about the question. Leading, lagging, or UPF, none. Is the question is clear for you? Listen. This synchronous motor connected on the supply always, correct? Synchronous motor always connected on the supply. We are connecting on the supply. See, synchronous motor is connected on the supply. Okay, it is connected on the supply. DC excitation will be given. DC excitation compulsorily to be given. Yes, DC excitation is given. Okay, yeah. Listen. Under no load condition also, will it draw the current or not? Definitely it will draw. Definitely it will draw. But this is voltage. This is voltage. And it will draw the current. No load condition also, it will draw the current. IA not say. No load current. Armature flux exists. Rotor poles are there, na? Rotor poles are there. North pole, south pole say. Two fluxes are there. no load condition current is not zero, dear students. No load condition current is not zero. It will draw some current that may be lagging or leading, depends upon what? Depends on the excitation. Excitation. This field current is there, na? Yeah. If you over-excited, machine is over-excited, that is said to be leading power factor. If motor is under-excited, lagging power factor. The power factor is angle between this voltage and current, supply voltage and current. That lagging or leading, you have to identify. And he is giving field current constant. Field current is constant. Okay? Yes. What is the answer? That we have to verify. Okay. The data given in terms of what? Flux. Fluxes is giving when armature corrected 25 milliwebers. When disconnected, how much? 20 milliwebers. With that way, we have to see. Okay. Listen. When the armature is connected on the supply, net flux is equal to how much? Phi R is equal to phi M plus or minus phi A. That is equal to 25 milliwebers. I don't know, plus or minus. Plus for lagging power factor, minus for leading power factor. But when armature is connected to the supply, when armature is connected to the supply, when connected to the supply means armature current, it will draw the current, then only motor will rotate. Then only motor will rotate. We don't know, plus for magnetization, minus for demagnetization. Okay. And when disconnected, what is the air gap flux? Phi M. What is phi A? Phi A 0. When armature is disconnected, say, when I am disconnecting this, when it is disconnected, armature is disconnected. What is the current? Then this current is going to be 0. Current 0. When disconnected, current 0. Armature flux is also 0. So at that time, phi M only exists. Phi A 0. Phi A 0. That is equal to 20 milliwebers. When armature is disconnected from the supply. When armature is disconnected from supply. Disconnected from supply. Flux is equal to phi A is equal to 0. Why? Since IA is equal to 0. Phi A is equal to 0. This part is going to be 0. No armature flux. Only main field flux. Now tell me. Compare both equations. Listen. By comparing both relations, phi M is, it is identified phi M is 20 milliwebers. Second case, phi R is equal to only phi M. Phi R means air gap flux resultant. One flux is 0. Phi M is equal to 20. Phi M is equal to 20, but phi M and phi A together 25. Phi M and phi A together 25 means is the phi A is aiding or opposing? Phi A is aiding. Together. Two fluxes, 25 milliwebers. Phi M is only 20, phi M plus phi A. It is 5 plus. So by observing above relations, we can say phi A is aiding with phi M. Phi A aiding with phi M. Therefore, what is armature reaction? Armature reaction is magnetization. When armature reaction is magnetization, what is power factor? Tell me. Therefore, power factor for motor, lagging power factor. Lagging power factor. For motor, it is lagging power factor. So answer is A. Lagging power factor. Lagging power factor. Fine. Now, right. So these type of questions, even ESC examination he has given. Not in terms of Webers. When connected, it is phi M. When disconnected, it is 3/4 of phi M. 3/4 of initial case means reduce. Okay. Now, Before going to next topic, I would like to show. Right now, I have shown with the phasors. Now I have shown with the phasors. I would like to show with phasor diagram, physical diagram. Physical diagram, how exactly it is magnetization, demagnetization. I will show only for 1 or 2 diagrams, and you can able to understand very clearly. See. Now, how to draw the phasor of EMF and current. How to draw the phasor of EMF and IA and current IA. Let us see. In this, I would like to show E lags flux by 90 degrees. E lags flux by 90 degrees. And how? How E lags phi by 90 degrees. By 90 degrees. With this diagram, I would like to show. See. Physical diagram. Okay. This is 2-pole machine, North Pole and South Pole. North Pole and South Pole. One conductor, this is another conductor. One conductor, another conductor. Flux direction. Flux direction, this is the flux direction. This is the flux direction. Flux direction. So this is the flux. Phi m. So phi m phasor is here. Phi m phasor is in this direction. This is the phi m. Main field flux. Phi m or Fm. This is along d axis. D axis. This is d axis. D axis. Okay. When that is d axis, rotor is rotating in counterclockwise direction. When rotor is rotating in counterclockwise direction, I am taking counterclockwise direction. When rotor rotates in counterclockwise direction, what is the current in this conductor? And a north pole, what is the current? North pole current is dot. South pole it is cross. Okay. Yeah, see. North pole, south pole. This is flux direction. Flux direction is from north to south. And this is also north to south. Okay, yes. So these are the flux directions. So main field flux is, let me remove this because I need some space. This board is very small. Okay. See, this is flux direction. Flux is in this direction. This is the flux direction. Main field flux direction, phi m or Fm. That is said to be d axis. D axis means polar axis. There is a polar axis. Direct axis is nothing but what? polar axis, center of the pole. Center of the pole. That is the main field flux. Main field flux. Rotor is rotating in counterclockwise direction. When rotor is rotating in counterclockwise direction, if there are two conductors, this conductor 1 and conductor 2, say conductor 2. So under north pole, what is the current? Flux direction. When conductor is moving, it is flux is thumb upwards, current is outwards. Under south pole, current is outwards. What is the current here? Cross. Okay. Why? Because rotor rotating counterclockwise, but conductor is assumed to be rotating opposite. Conductor is on the stator. Conductor in the stator means, so under north pole is moving downwards at that instant, say, conductor is moving upwards, current is outwards, dot and cross. But in this, can I say EMF is maximum? Yes. EMF will be maximum in this conductor, which is existing under the north pole. EMF is maximum value. EMF is maximum. EMF is maximum. When conductor is under the pole, EMF always maximum. Maximum value of EMF takes place only under the pole, direct axis. This is, I would like to take for unity power factor. Let us say for unity power factor, for UPF. For unity power factor, the diagram we are drawing, unity power factor. For unity power factor, current also maximum here, na? Current also maximum in the same conductor. IA also maximum. For unity power factor, IA also maximum. This for what? For UPF. For UPF, E maximum and IA maximum, both will be in same phase. Both will same phase. Both will at same instant. Both will same phase. Huh? Yes. Both are in same conductor. Both are in same conductor. Both are under the. Both are along the direct axis. Both are along D axis. The EMF is maximum means current also maximum. Current also maximum. Okay. Current maximum. Now, if you want to show the current phasor, how to draw? Current phasor means current will produce the MMF. To find the MMF, what to do? Apply your thumb rule. Current entering this side, right side current entering, right leaving. This is thumb direction. Thumb is in this direction. Thumb direction. So MMF due to, I mean to say, this is MMF due to armature flux. FEA, say this is FEA. Armature MMF. And this is also armature flux. Armature flux. When that is armature flux means, can I say armature current this is? Yes. This is armature current. MMF is proposed in phase with, this is phi A, sorry, phi A. Armature entering, leaving. This is the armature MMF, flux in this direction. Armature MMF also. When MMF in that direction means current phasor also there. Current phasor. Current phasor. These are instantaneous values. I maximum. But to draw the phasor, apply the thumb rule. Entering, leaving. That is the current. Now to find the EMF phasor, again apply the thumb rule. E cross E dot. Apply the thumb rule. That will be E. So E phasor will be here. E also here. E, why? Because this is E. This is also E phasor. E phasor. So therefore, if you take these two, how E lags the flux by 90 degrees. 90 degrees. And for unity power factor, both are in same phase, na? UPF. Both are in same phase. So to draw the phasor, apply right hand thumb rule. Right hand thumb rule. Thumb rule. Right hand thumb rule. Right hand thumb rule. Find the MMF. Find the MMF. Find the flux or MMF. Find the flux or MMF. Find the MMF. That is itself. That is itself. Current phasor. That is itself current phasor. Or EMF phasor. EMF phasor. Thumb rule you have to apply. EMF phasor. Now I will take next 0.8 lagging power factor. Say, if I take 0.8 lagging power factor, this is over, na? Simply thumb rule. Right. Now, take a unity power factor. This is for which power factor? UPF. This is for unity power factor. This diagram is for UPF. Whatever we have drawn for UPF. This entire diagram is for UPF. Now, let us see for 0.8 lagging power factor. 0.8 lagging power factor. For 0.8 lagging power factor, North pole, South pole. This is one conductor, one conductor. Flux is in the same direction. This is the flux direction. Flux directions. These are the flux. Main field flux is same only. This is same. Pi m. Fm, that is fixed. This phasor is fixed. And the phasor we are extending outside. Don't think flux is not coming outside. Yes, student. We will take return path. But for visibility, we are showing the phasors outside. Outside. Okay. Yeah. Now. Always the current, they are rotating in counterclockwise direction. They are rotating in counterclockwise direction. In this it will be cross, in this it will be dot. Maximum value. This is E maximum. E maximum. This is also dot E maximum. Dot E maximum. Fine. Cross E maximum, dot E maximum. And when I want to draw for 0.8 lagging power factor, say, if I want to draw for 0.8 lagging power factor in the case of generator, this diagram is for that. When EMF is maximum, when they are rotating in this direction, now I can say current will be maximum at an angle of IA maximum. IA maximum. E maximum to IA maximum, angle will be maximum values only I am taking. Angle is, that is a power factor angle. Is a power factor. What is the angle between both? 36 degrees. 36 degrees angle. Cross dot cross. And similarly, this is dot na. This will be the dot. Current maximum. Is also lagging na. It is also lagging. Lagging. And here also it is lagging. The current is lagging. Current lagging. Okay. Are you getting? Counterclockwise direction you need to take. When if you take counterclockwise direction, see, this is voltage. His name is voltage. Right? Is moving in this direction. Is moving in this direction. Right? And current is also is a current. Current also moving in this direction. Same direction. Who is lagging? Tell me. Red color is lagging, na? He is lagging compared with this person. Both rotating. He is going back. Is lagging. So IA maximum lags. IA maximum lags E maximum by 36 degrees. Right? 36 degrees. E lags max, IA maximum lags the E maximum. That's all. Some angle. Are you getting? Here cross maximum and here cross maximum. Both rotating in counterclockwise. Cross of the current lags the cross of the voltage by some angle. Okay? Yeah. Now, then to draw the phasor, what to do? EMF phasor, apply the thumb rule. Current is EMF is always maximum under the pole only. Whatever may be the power factor. Armature current is there. Na? Current phasor changes. Phase changes, current phasor. But EMF phasor always same. Because always under the north pole EMF is maximum. South pole maximum. Apply the thumb rule. Entering, leaving. So this is the MMF. This is fixed. This is EMF phasor, it is fixed. This is EMF phasor. That will be always along the Q axis only. Q axis. Now apply your thumb rule for current. Current is maximum here. Entering, leaving. When entering, leaving means this is the MMF. Armature MMF in this direction. Yes, this is the armature MMF. FA and also IA. This is FA and IA. This is IA. This is also FA. Current lagging, no? IA lags. IA lags the V. It's a current phasor. Current phasor. Lagging. Current lags the voltage with some angle. In the same way, lastly, okay, why I am explaining, if you read some standard textbooks, they will draw the phasors on the diagram. Okay, here also same, north pole and south pole. Now I want to show how it is exactly demagnetization, magnetization. North pole, south pole. Flux direction is from north to south. This is one conductor. If you take, this is a conductor. This is also conductor. Flux direction. This is the flux. Diagram is same. So flux. Rotor is rotating in counterclockwise direction. Counterclockwise direction. This is phi m. Phi m is fixed. Phi m is same. This phi m. Phi m. Of course, in this conductor always cross E maximum, and here it is always dot E maximum. Dot E maximum is here. Okay, that is fine. Now I want to draw for ZPF lagging. Now you have to say ZPF lagging. For ZPF lagging, where is the current? ZPF lagging, the current will be here. Cross IA maximum. IA maximum. IA maximum. IA maximum lags, no? Lags. So if you compare, this is moving in this direction and current also moving in this direction. Current is moving in this direction. So this person lags this person. Is lagging. Lags this person. By how much? 90 degrees. 90 degrees. ZPF lagging. Cross lags cross by 90 degrees. Similarly, dot lags dots by 90 degrees. 90 degrees. Now you apply your thumb rule. Thumb rule, which direction it will come? Current lagging. Applying here, what is going to be happen? Actually, main field flux is in this direction, main field flux direction. This is the main field flux direction. Main field flux is in this direction. This is the main field flux. Okay, main field flux. Main field flux. Main field flux. But what is the direction of armature flux? This is for ZPF lagging we are taking. Apply thumb rule. Thumb rule means armature flux is in this direction, exactly opposite direction. Armature flux is exactly opposite direction. This is the direction of the armature flux. Armature flux. Okay. This armature flux. Phi A will be in this. Now, how both are there? Main field flux is in this direction. Main field flux direction is in this direction, but armature flux exactly opposite. So, phi A opposes phi M. Phi A opposes phi M. Opposing phi M. Therefore, what is armature reaction? Armature reaction is purely demagnetization. Armature reaction is purely demagnetization. Purely demagnetization. Because phi M, phi A opposes phi M. Phi A opposes phi M. Yes. So armature reaction is purely demagnetization for ZPF lagging. For ZPF lagging we have taken. Okay. Yeah. In same way, you can also check for ZPF leading. For ZPF leading, what is going to be happen? Cross will on the top of the conductor and bottom side of the conductor it will be dot. This is voltage, this is current lagging, both rotating in counterclockwise. Current fellow. His name is current, his name is voltage, say. Voltage, current. Current lags the voltage, na? Yes. Both rotating. Blue color is voltage, red color is current. Red current fellow is lagging the blue color fellow, current lagging. If ZPF leading, if you take, this cross will leads here. When if you take leading, this cross is there, it is going to become to here. It will be here. This is cross of the current will be here. This is dot of the current. Then how it is? Entering, leaving. This is a flux. Same direction. Flux will be the same direction. Aiding purely magnetization. Okay. That is the physical diagrams. That is exactly what will happen inside of the machine. Now you can check for any power factor. I have drawn for diagram for exactly 90 degrees. Lagging. Even this phi A also there, no phi A, we can divide this into two components. Lagging power factor, this one component and this one another component. It causes demagnetization and this causes cross magnetization. Okay, fine. Now lastly, see. Armature reaction. Armature reaction can be represented. Armature reaction causes drop of voltage and also rise of voltage, na? Drop and rise. But drop due to armature reaction is equal to represented in IARA. IAXCS. Drop due to armature reaction. Drop due to armature reaction is equal to IA into XA. IA into XA. Where XA is a fictitious reactance. Where XA is a fictitious reactance. Fictitious. That is imaginary. Imaginary reactance. Fictitious reactance. And that XA is called armature reaction reactance. Called armature reaction reactance. Armature reaction reactance. Or it is also called or magnetizing reactance. Magnetizing reactance. or it is also called demagnetizing reactance also. Demagnetizing reactance. Okay, we will go for a break just after 5 minutes. So with that, armature reaction is going to be completed. And after that, we will start with another topic. Yeah. Listen. The armature reaction causes some drop of voltage, no? Yes. Armature reaction causes some drop of voltage or rise. Normally, it is causes drop because power factors are lagging power factors. Lagging. But how you can represent the drop? The drop can be represented either in a resistance or reactance. Two elements are there, resistance or reactance. Modeling, it is called what? Modeling. XA is a fictitious reactance we have to model. I think you will know it. The force voltage analogy. Any mechanical system can be replaced with electrical system, equivalent. Any mechanical system can be modeled with equivalent electrical system. You can draw the equivalent circuit for transformer, equivalent circuit for induction motor. You can also draw equivalent circuit for DC motor also you can draw. But you are not drawing. At least you may know a control system force voltage analogy. A mechanical system force analogous to in mechanical system, what is that? Mechanical system force analogous to electrical system voltage or current. Force can be replaced with voltage or current. Mass in mechanical system can be replaced with inductance. Elasticity property in mechanical system can be replaced with the capacitance. Friction in mechanical system can be represented with the resistance in electrical system. Modeling. Friction is modeled with a resistance because where friction is there, frictional losses. Where resistance is there, I squared losses. Where frictional losses are there, heating effect. I squared losses also, they will produce the temperature. Modeling. Same way, armature reaction also can be modeled with a fictitious reactance XA. Fictitious reactance XA. Here the point is, why only represented with reactance? Why not IA into RA? Why not I for armature reaction? That is called IA XA you are showing. But why not IA into RA? Already RA there, or you can say RA dash. But it is totally wrong. No. It must be only reactance only, correct. Not resistance. Drop can be represented in resistance or reactance, but resistance is not the suitable component. Reason is armature reaction causes only drop of voltage. Due to armature reaction only drop of voltage, but no power loss. Due to armature reaction, no power loss. And it depends on the power factor. Reactance only suitable. If you take resistance, drop is there, drop of voltage. But where resistance is there, copper loss also takes place, losses also. But armature reaction does not causes any power loss. So resistance cannot be represented. Armature reaction represented with resistance, power loss is there, but armature reaction does not causes any power loss. So suitable component is only reactance. That is also question in examination how you will ask. Armature reaction is modeled with A bit to resistance, B bit to reactance, right? And C bit some other thing. A bit resistance, B bit reactance, C bit inductance, D bit capacitance. What is that? Reactance. It may be inductive reactance or it may be capacitive reactance. Reactance is suitable component. Let me show. Reason. Why armature reaction is represented? Why drop in armature reaction? Drop due to armature reaction is represented in resistance. Is represented as drop in reactance. Drop in reactance. Let us see. Reason is, the reason is armature reaction causes armature reaction causes only drop of voltage. Only drop of voltage, but no power loss. But no power loss. Power loss. And it depends on the power factor of the load. Power factor. Therefore, the suitable component for modeling the armature reaction is a fictitious reactance. Imaginary. Modeling fictitious reactance. Okay, that's all. Fictitious reactance. You will say drop due to armature reaction is modeled with a bit fictitious resistance, fictitious inductance, fictitious capacitance, fictitious reactance. It will be fictitious reactance. Right? So with this, we are completed armature reaction. Now let us take the break. After that, we are going to start another topic. So break is for 20 minutes. 20 minutes. Break for 20 minutes. Class will start at 7:47. Now it is 7:27. 7:47. Okay. 7:47. Okay. Topic is causes for drop of voltage. Okay. This is about armature reaction. Now, let us move to the next topic, that is causes for drop of voltage. Causes for drop of voltage. Causes for drop of voltage. There are three causes for drop of voltage. Number one, drop due to armature resistance. Drop due to armature resistance, that is said to be IaRa drop. IaRa drop. IaRa drop. Resistance drop. Next, drop due to armature leakage reactance. Armature leakage reactance, that is IaXL drop. IaXL drop. Third one is drop due to armature reaction. Drop due to armature reaction, that is IaXL drop. IaXL drop. Drop due to armature resistance, drop due to leakage reactance, drop due to armature reaction. IaXL drop. Fine. You know, resistance means every winding is made with copper. Winding is made with copper. Where copper is there, resistance drop takes place. Where copper is there, resistance will take. Resistance drop takes place. And how that resistance measurement, resistance can be measured. Measurement of resistance, see. Measurement of Ra. Measurement of Ra. Measurement of Ra. How armature resistance is measured? Measurement of armature resistance. Alternator is star connected, no? Yes. Alternator is star connected. We will supply a DC voltage here. This is ammeter. DC voltage. DC supply. And this is voltmeter. Voltmeter. Plus minus. This is armature current. This is voltage V. Or ammeter reading and voltmeter reading. Now, this is the current, no? This is armature current. This is the current, IA. This is armature resistance. This is armature resistance. But we are open circuited. Other side, it is open circuited. RA. So therefore, what is to RA? RA plus RA. RA plus RA into IA. That is equal to voltmeter reading. Or RA plus RA into ammeter reading is equal to voltmeter reading. So therefore, 2 RA into ammeter reading is equal to voltmeter reading. So therefore, RA is equal to how much? RA is equal to voltmeter reading divided by 2 into ammeter reading. 2 into ammeter reading. But this is RA DC. What is this? This is RA DC. Whereas RA AC is equal to RAAC effective resistance is equal to 1.2 to 1.3 times that of the RADC. And 1.6 times of RADC for high frequencies. Okay. The AC resistance is more compared with DC resistance. RAAC is more compared with RADC. What is the reason? Reason is skin effect. Reason is skin effect. I think you may be knowing these things. Skin effect. AC resistance is more compared with the DC resistance. Okay. Yeah. This is for star connection. Similarly, if you want to find for delta connection, how to measure delta connection? Delta connection also. For delta connected armature, RA. Here we are applying DC again. DC plus minus. You have to apply only DC. If you give AC, what will happen? Voltmeter reading by ammeter reading, that will give you the impedance. Okay. Impedance. That's the reason it has to be given only DC. When DC is there, reactance becomes 0. DC means reactance 0. So it gives only resistance. This is RA, this is RA, this is RA. This is open circuited. Now what is the resistance? You apply. This is one path, na? Current, this is one path, and another path is in this direction. Is another path. Another path is in this direction. Therefore, the resistance will be RA plus RA. RA plus RA in parallel with RA. That is equal to voltmeter reading divided by ammeter reading. Equivalent resistance, no? Ammeter reading. That is 2 RA parallel with RA is equal to voltmeter reading by ammeter reading. And 2 RA means 2 RA into RA divided by RA plus RA. That is equal to what? 2 RA square by 2 RA, no? Yes, sorry. RA into RA, 2 RA plus RA, that is 3 RA. That is equal to 2 by 3 into RA. But what is RA? RA DC. RA is equal to, RA DC is equal to how much? How much? It is 3 by 2. Okay, na? Yeah. 2 by 3, na? Yes, 2 by 3 into RA. But RA is equal to 3 by 2 into voltmeter reading divided by ammeter reading. So resistance and reactance, it can be measured with voltmeter and ammeter reading. But sometimes you may ask, what is the resistance? The voltmeter and ammeter is connected directly. Most of the times he will give RA. Indirectly data given, you are supposed to find the resistance means with this method. Okay. Yeah. Now. And all the drops. These are the 3 drop of voltage, na? Drop due to resistance, drop due to reactance and all. But drop due to leakage reactance and armature reaction, both will be in same phase. Drop due to armature reaction, drop due to leakage reactance, drop due to IAXL. Drop due to XL and XA will be in same phase. Both are reactants, na? Will be in same phase. Therefore, XL and XA can be additive. That XL plus XA, that can be called as XES. This is said to be synchronous reactance. Synchronous reactance. XL plus XA is called synchronous reactance. Synchronous reactance. Synchronous reactance. Total reactance of synchronous machine. So synchronous reactance is the sum of leakage reactance plus armature reaction reactance. Similarly, RA plus JXES. RA plus JXES, that is called what? ZS. ZS. This is said to be synchronous impedance. This is synchronous impedance. Impedance of synchronous machine. Synchronous impedance. Impedance of synchronous machine. This ZS can be written. RA ZS is there, na? RA ZS. Among all these drops, see, among all these drops, IA-RA drop will be IA-RA drop 0.01 per unit. IA-RA drop. IA-XCL drop 0.15 per unit. IA-XCL drop is 0.15 per unit. IA-XCA drop is 0.84 per unit. 84 per unit. Right? From this, these are the practical values. Practical values. IA-RA 0.01 per unit. IA-XCL. Leakage reactance drop. Just like induction machine transformer you have to see, na? Leakage reactance drop. Here also it is the same. I don't want to explain that. But which drop is maximum here compared with? Yeah, armature reaction drop is much more. Drop due to armature reaction. Armature reaction is more. Resistance drop can be neglected. IA-RA drop can be neglected. Most of the times it can be neglected. It is given, we can take since it is very small. Since very small, drop due to resistance is very, very less. Can be negligibly small. Neglected. Next. RA. See, ZS. ZS is equal to RA plus JXES. And its magnitude is RA square plus XS square. Angle is called theta. Theta is equal to tan inverse of XS by RA. Tan inverse of XS by RA. Where theta is impedance angle. Theta is the impedance angle. Winding impedance angle. Theta is equal to tan inverse of synchronous reactance by resistance. That is impedance angle. And theta is nearly equal to 90 degrees. Nearly 90 degrees. Practical it is 80 to 85 degrees. Since RA very, very small compared with XES. Okay. RA is very, very small compared with XES, no? Yes. If RA neglected, theta 90. If RA is 0, say, then theta is 90. Practical values 80 to 85 degrees. And if you draw the drop, this is resistance drop, no? It is resistance drop, RA. Resistance drop. This is reactance drop. This is RA. This is XES, JXES. What is this? This is ZS. Impedance triangle. This angle is theta. This angle is theta. Theta is equal to tan inverse of XS by RA. Theta tan inverse of XS by RA. But cos theta, we can find here, cos theta is equal to RA by ZS. Therefore, RA is equal to ZS cos theta. Similarly, sin theta is equal to XS by ZS. Therefore, XS is equal to ZS sin theta. ZS sin theta. ZS sin theta. So have the idea about all these things. Have the idea about all these things. All these are important. Okay? Yes. Fine. Now having idea about all these drops, now we are ready to draw the phasor diagram of alternator. Phasor diagram of alternator. Let us draw the phasor diagram. Phasor diagram of alternator. Taken this? Yes. Phasor diagram of alternator. Phasor diagram of alternator. This is alternator. Alternator supplying to a load. Supplying to a load. This is a load. Load say. This is alternator. P phase load. Field current. We are rotating the field in clockwise direction. Take down fastly. Okay, this is the alternator. This is the load. And what is the load power factor? Say this is RL and this is XL. Then phi is equal to load power factor angle. Phi is equal to tan inverse of XL by RL. That is the load power factor angle. So phi is the load power factor angle. That is the load power factor angle. Load power factor angle. But machine angle is there. Na? Machine also will have some resistance and also reactance. That is theta. Theta is equal to tan inverse of XS by RA. But whereas theta is equal to tan inverse of XS by RA. That is said to be impedance angle. There is a lot of difference between phi and theta. That should be clear. Phi is load power factor angle, load resistance, load reactance by load resistance. Theta is the impedance angle. A machine angle, it is related to machine. Impedance angle. Machine related. Okay. See, when we have given DC excitation, it is producing the flux, and when machine is rotating, it will generate the voltage E. Say it's generate the voltage E. If example E some 450 volts, say 450 volts, 450 volts, then what is the terminal voltage? Terminal voltage also same 450 volts. No load condition, E and V same. No load condition, E and V same. Fine. Terminal across the terminal you measure, both are same. Under no load condition, no armature reaction now. Correct? There is no armature reaction, no armature current. Generated EMF is E, 450 volts. That is proportional to main field flux. E proportional to phi m, main field flux. DC excitation. Now connect the load on that. Now connect the load on this. Load is connected. When load is connected, load current, armature current will comes into picture. Okay, that current only going here, na? Yes. Load current is coming into picture. Due to load, what will happen? Current, it is produces armature flux in opposite direction. Correct? It produces armature flux in opposite direction. The net flux will decrease. Net flux is decreases. When net flux decreases, net generated EMF also decreases. That we will call ER. ER is equal to some 430 volts, say. 430 volts. Why that voltage is decreasing? That voltage is decreasing because of armature reaction. Due to demagnetization, when load connected, armature flux opposes, net flux decreases, therefore generated EMF also decreases. Right? I hope this is clear. E is proportional to main field flux, but ER is proportional to phi R. Phi R is equal to how much? Phi M minus phi A. So net flux is reduced. Na? That is called air gap voltage. This is called air gap voltage. Why air gap voltage? It is proportional to air gap flux, area of flux. ER is the generated EMF under load condition. Dear student, ER is the generated EMF under load condition. E is the generated EMF under no load condition. No load condition, no armature reaction. That's the reason E is the 450. But when load connected, armature flux is coming into picture. It is opposing. Therefore, net flux decreases. When net flux decreases, generated EMF also decreases. ER. And that to be coming to the terminals, what is going to be happen? Terminal voltage still decreases. Terminal voltage still decreases. It may be some 400 volts, say 400 volts. V still decreases because resistance and leakage reactance, it will be still decrease, still reduce. So I can draw the drop like this. E minus ER. E no load condition 450, ER 430. Na? Now can I say E minus ER is equal to IA into XA drop? Yes, IA into XA drop. E is the generated EMF under no load condition. Generated EMF, no load condition. But this is generated EMF under load condition. Load condition. Load condition. The armature reaction, after armature reaction, it could be reduced. So therefore, E minus ER. If you draw the equivalent circuit of this, the equivalent circuit is, this is E generated EMF, E. This is armature reaction drop. This is J into IA XA. J into XA. J into XA. Now this is air gap voltage. This is armature current. E minus IA XA. E minus IA XA is equal to, this is ER. 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 Now again leakage reactance. JXCL. And resistance. Resistance. We are connecting the load to this load. Okay, RE. This is V. V is nothing but terminal voltage. V. This is a load. This is equivalent circuit of alternator. Equivalent circuit of alternator. This is equivalent circuit of alternator. First E na generator EMF is E. When load connected due to armature reaction, net voltage decreases. That is ER. That minus IAXL and IARA is nothing but V. And from this diagram, if I want to write equation E is equal to, you come from this side, E is equal to V plus IARA, IAXL and IAXA. Correct? This is the current is going, say. What are the drops? I am coming from V. E is the higher potential, E higher potential. So to obtain E, from V you have to come V plus all the drops, V plus IARA plus IAXA, IAXA. So let me write the equation. E is equal to E. E is equal to V plus IARA plus J into IAXL plus J into IAXA. That is equal to V plus IARA plus J into IAXL plus XA. That is equal to V plus IARA plus J into IAXS. That is XES, no? Yes. Which is equal to V plus IA into RA plus JXES, which is equal to V plus IA into ZS. So E is equal to V plus IA into ZS. Finally, you have got E is equal to V plus IA into ZS. Okay? Yeah. Phasor diagram is nothing but by adding all these things, you can frame a phasor diagram. If you add V plus IARA plus IAXL, that is going to be phasor diagram. And one more point here is E leads in generator. In generator, E leads V. In generator, E leads V. E always leads the V. E leads the V by delta. We can say this is by delta. E leads the V. In generator, E leads the V. Reason why E leads the V. Let me take this discussion on this side. I need some space. Okay. Why? E leads in generator. In generator, E leads the V. E leads the V by delta, by angle delta. Reason is, see, reason is impedance drop, due to impedance drop. Reason is impedance drop. Due to impedance drop, E leads the V. So for example, if you take V at an angle 0, for example, see, V is equal to 1 per unit at an angle 0, 1 per unit at an angle 0. And IA is equal to 1 at an angle, some minus 36.86 degrees. That is itself 5, load power factor angle. Similarly, ZS say, ZS is equal to how much? 1 at an angle, some 80 degrees say. 1 at an angle 80 degrees. Right? Yes. Now what is E? E is equal to V plus IAZS. That is equal to V1. 1 at an angle 0 plus IA. IA is equal to 1 at an angle minus 36.86 into ZS. 1 at an angle 80 degrees. So you will get E value will be some value, V will be some other value. E and V. What is that? Can you calculate? Any one of you? Any one of you and tell me what is the E value? E is equal to how much? 1010. What is that value? Any one of you? What is that value? Anybody calculated? 136 minus. How much magnitude? Magnitude, tell me. Any one of you? Do you have a calculator and calculated? 1.85. Okay. 1.55. What is angle? Ashish Raj. What is its angle? Angle. 1.85. Angle how much? Angle calculate and tell me. Angle is very good. 21.5. 21.57 degrees. That is itself delta. That is itself delta. So V0 means, therefore E leads V by delta. Always in generator, E leads V by delta. In this example, 25.57. You take any lagging power factor, leading power factor, whatever it is taken, definitely E will be leads V by delta. That's the reason V0 na E delta. Delta is called load angle, or it is also called angle behind synchronous impedance. Angle behind synchronous impedance. Delta is called load angle or power angle, or it is also called angle behind synchronous impedance. Angle behind synchronous impedance. Angle behind synchronous impedance. Okay. Angle behind synchronous impedance. Why? Because you see E and V is there, na? E and V is there. V is at an angle 0. V is 0 only. But why phase difference is coming for E? That is because of IAZS drop. What V0? E coming angle, the difference is due to drop. Mainly due to drop. Okay. In earlier diagram, if you see V at an angle 0, if you take, E will be at an angle delta. So that's the reason it is said to be angle behind synchronous impedance. Angle behind synchronous impedance. This is all synchronous impedance, na? It's all synchronous impedance drop. So therefore, angle behind synchronous impedance. Angle behind synchronous impedance. Okay, like this is E, na? This is E. This is total ZS I can take now. This is RA plus ZS. This is V. V will be at an angle 0. This is ZS. This will be E at an angle delta. So behind. This is 0, say, behind it. This delta is coming. Angle behind synchronous impedance. Yeah. Now, so having idea about all these drops, now let me draw the phasor diagram of alternator. Phasor diagram of alternator. Phasor diagram of alternator. To draw the phasor diagram, see, this is phi m. Phi m or FEM also you can take. Phi m, FEM both are same, na? Phi m is the flux MMF. Flux is equal to M by reluctance. MMF flux both will be in same phase. Which direction both are said to be? Direct axis. They are said to be along the direct axis. D axis. They are on D axis. Now induced EMF will be along the quadrature axis. It is decided induced EMF will be along the quadrature axis. So E is going to be here. E is along the quadrature axis. I will come to the tip of E where it will be, but D will be along the quadrature axis. V will be lags, na? V lagging. V lags E. V lags. V lags. This is V. Angle between E and V delta. V. This is IA, say. IA. Armature current IA. All phasors are rotating counterclockwise. Then E lags V. IA, lagging power factor, I am taking IA. This is IA means IA RA. This is IA RA, correct? Yes. I am adding to the V. V plus IA RA. V plus IA RA. That will be IA RA drop is in phase with IA. In phase with IA. And this is said to be IA axial drop. This is IA axial drop. IA axial drop. Now this is IA axial drop. IA axial drop. IA axial drop. So finally this is E. By adding all the drops, this is E. This is IA axial drop. IA axial drop. So E is along the Q axis. E is along the quadrature axis. Quadrature axis. Okay. This is IA ZS. IA ZS. IA ZS. IA ZS. Okay. This is the phasor diagram. Phasor diagram of alternator. And ER is equal to V plus IA RA plus IA axial. If you see from this diagram, what is that ER? Can I write ER is equal to V plus IA RA plus J into IA axial, correct? ER is equal to V plus IA RA plus J into IA axial. IA axial also correct. ER is equal to, right? So if you draw the phasor from the phasor diagram, V plus IA RA, IA axial. This is V, IA RA, IA axial. Now this will be the ER. This will be the ER. So this is ER. This is the ER. 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 Okay. This is said to be ER. Air gap voltage. It is air gap voltage. Why it is called? Reason is IA First, let me write. This is the delta. Delta is the angle between E and V. This is the delta. And this is phi. This is psi. Psi is the angle between E and IA. So, delta. E is called what? Generated EMF. E is generated EMF under no load condition. Generated EMF under no load condition. No load condition. It is also called excitation EMF. Also called excitation EMF. V is a terminal voltage. V is called terminal voltage. V is terminal voltage. And ER is equal to V plus IARA plus J into IAXL, or that is also same as E minus J into IAXA is same. But that is called what? Air gap voltage. Air gap voltage. Air gap voltage. Delta is the angle between E and V. That is called load angle. Load angle or power angle or angle behind synchronous impedance. There is a question in GATE of 2013. Is asked angle behind synchronous impedance. You need to calculate delta value. Angle behind synchronous impedance. And phi is the angle between V and IA. That is a load power factor angle. Load power factor angle. Load power factor angle. Okay. Yeah. And psi is the angle between E and IA. It is internal power factor angle. Internal power factor angle. Internal power factor angle. Internal power factor angle. Psi is equal to phi plus delta. In this, what is psi? Psi is equal to, you are getting phi plus delta. Okay. See, this is IA, na? This is IA. This is ISA, and phi A will be, phi A is in same phase. This is phi A. Now take resultant of phi M and phi A. Take resultant of phi M and phi A. Phi M and phi A. This is called phi R. This is said to be phi R. Resultant flux, phi R. Phi R or FR. Phi R. Phi R or FR. Phi R or FR. Angle between this and this is equal to, the angle between these two is delta. This is 90 degrees. But at the same time, angle between this and this is equal to 90 degrees. 90 degrees. And ER is perpendicular to phi R. ER is related to phi R. E related to phi M. E lags phi M by 90 degrees. Similarly, ER lags phi R by 90 degrees. Okay. This is a phasor diagram. Now, why I am drawing all these things? I will give the questions now on this. Tell me. The question is like this. Question is on this question, angle behind the phase angle between armature MMF and main field MMF in alternator is A bit 90 degrees, B bit 90 plus psi, C bit 90 minus psi, D bit psi. Tell me the answer for this. The phase angle between armature MMF and main field MMF in alternator is, what is that angle? This is your previous examination question. Main FM and FA, you have to find FM and FA. See what is angle FM and FA? Of course, this is itself FA na FA. FM and FA angle is, yeah, this is 90 and this is psi. Psi, no? 90 plus psi. From the phasor diagram you can find 90 plus psi. 90 plus psi. This is 90 and this is psi. Correct? This is the psi. 90 plus psi. This is psi. So your answer is 90 plus psi. Just make a note there. In synchronous motor, angle between main field MMF and armature MMF is 90 minus psi. It will be 90 minus psi. But motor it is 90 plus psi. 90 plus psi. Okay. Similarly, see another question. Angle between main field MMF and terminal voltage V. Terminal voltage V is dash. What is the angle? Tell me. Angle between main field MMF and terminal voltage, how much? Terminal voltage, main field MMF. See, this is V. V2. Here it is 90. Phi M to E 90. E to V delta. E to V delta. So, answer is 90 plus delta. 90 plus delta. Okay? 90 plus delta. Similarly, another question. Your examination, previous examination, in an alternator, an alternator supplying for lagging power factor of 0.707 lagging. Is supplying for a lagging power factor of 0.707 lagging. Right? The angle between E and B is 15 degrees. Then the phase angle between main field MMF and armature MMF is A bit 90 degrees, B bit 135 degrees, C bit 150 degrees, D bit 45 degrees. Huh? 45 degrees. Huh? Answer? Answer is 150 degrees. Correct? 150. Here, what is 5? 5 is 45 degrees. No? 5 is equal to 45 degrees. Since 0.707 lagging, that is 5. Okay. Then delta 15. Delta 15. So psi is equal to how much? Psi is equal to 5 plus delta. 5 plus delta. Earlier diagram you see 5 plus delta. 45 plus 15. 60 degrees. 60 degrees. But angle between phi m and phi a is equal to 90 plus psi. 90 plus 60 is equal to how much? 150 degrees. So your answer is 150 degrees. That is 150. Okay? 150 degrees. Okay? Yeah. This type of questions. In the same question, 0.707 leading, say, what is your answer? Points instead of lagging, 0.707 leading, your answer is going to be 60 degrees. It will be 60. For example, here let me add one more option. It is 60 degrees. Say, at that time, your answer is going to be 60 degrees. It's 0.707 leading if you take. Okay, like that. I hope you got the idea. Yeah. Now, clear? Okay. Yeah. See. Now coming to the final phasor diagram, it is like this. The phasor diagram is, from here onwards, I am not going to draw the MMF phasors. I have taken FEM and FA, all those things. Later onwards, I am not going to use all the things. Simplifying phasor diagram, only VE drop. That's all. See how simple we are going to make. This is E. This is E. E. This is V. V. And this is IA. IA. IA, RA. IA, RA. And this is IA, XES. IA, XES. IA, XES. IX is perpendicular. V, IA, IARA, and this is IA axis. IA axis is perpendicular to IA. Okay, this IA axis. This is V, E, IA XES. This much diagram is enough for us. IA ZS. IA ZS. This much diagram is enough. IARA. Okay. This is delta. This is a phi. Phi. And what is this? This is psi. Psi. Enough. This is a phasor diagram of alternator. And for simplification, see, in this diagram, I can divide V into two components. V into two components. This is V cos phi. V cos phi. And this is IARA. IARA. What about this? V sin phi. This is V sin phi. V sin phi. What is this? This is IAXES. IAXES. Now, from outer right angle triangle, if you take, E is the hypotenuse, no? E is the hypotenuse. E is the hypotenuse. Now, from the diagram, can I write this E hypotenuse? This is a right angle triangle. This is a right angle triangle. Therefore, E is equal to V cos phi plus IARA whole square, V sin phi plus IAXS whole square. This is square plus this square. E is equal to. So, therefore, E is equal to, from the diagram, E is equal to square root of V cos phi plus IARA. IARA whole square plus V sin phi plus or minus IAXS whole square. Of course, plus is for lagging power factor, minus is for leading power factor. Plus is for lagging power factor, minus is for leading power factor. So remember this relation, important relation. This is E. Okay. Another relation, tan psi. Let me write tan psi. Tan psi is equal to, in this tan psi, this angle, from this right angle triangle, opposite side, V sin phi plus IAXS, V sin phi plus IAXS divided by V cos phi plus IARA. Of course, this is plus minus. I am drawing phasor diagram for lagging power factor. No? Now I have drawn what is the phasor diagram is for lagging power factor. Lagging power factor. Lagging power factor means plus. Plus is for lagging power factor, minus is for leading power factor. Plus for lagging power factor, minus is for leading power factor. And another relation, psi is equal to phi plus or minus delta. Phi plus or minus delta. Plus for lagging power factor, minus is for leading power factor. Plus for lagging power factor, minus for leading power factor. Okay. Leading power factor. And even if you want, you can draw your phasor diagram also. I am taking E vertical now. Instead of that, if you are interested, you can also draw the phasor diagram like this. This is V reference, no? This is V reference, V. And IA, this is IA. Lagging power factor, IA. Now this is IARA in phase. This is IARA. V IARA. IAXES. Both, everything is same. IAXES. Now this is E. 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 Okay. What is this angle delta? This angle is phi. This angle is psi. Psi. Yeah. Now again, if you want, you can divide into two components. That can be divided into two components. Two perpendicular components. One component and this is another component. Okay. Yes. So what is this? This is V cos phi totally. V cos phi. Yes. This is V cos phi. This is IRA. V sin phi. And this is IAXES. Therefore, what is E? E. Equation same only. E is equal to square root of V cos phi plus IARA whole square. E is equal to, from this diagram also, E is equal to square root of V cos phi plus IARA whole square V sin phi plus or minus IAXES whole square. Both relations are same. And here I am taking V reference, but there E vertical have drawn. And if you shift this phasor counterclockwise, that only you will get. E, it is some angle, rotate some angle. E reference, E vertical. Okay. This is about the phasor diagram of alternators, right? In the next class, we are going to see the, okay, the next class we are going to see voltage regulation of alternator. Voltage regulations of alternator. Yeah. Now, in this class, any doubts are there? So it's almost 9 o'clock. Now, any doubts are there? You please ask. Yeah.
Hello, sir.
Hello. Tell me.
I did not find any changes in the flow diagram, sir.
Both are same. One textbook you can take like that, another textbooks you can see like that. I have drawn whatever I have drawn from PS Bimra notation. Actually, E will be taken vertical, that is a standard.
Okay, sir.
Both are same, no difference. Both are same.
And one more doubt, sir.
Both diagram are same.
Sir, IA value చాలా ఎక్కువగా ఉంటుంది కదా సార్. And why we are neglecting IRA, sir?
RA very less. IARA itself 0.01 per unit. And total drop it will be 1% ఉంటుంది అంతే. Among total drop it is just 1%. Though IA is more, IA rated value only we will take always. IA rated, IARA, IAX, current rated taken with IARA drop is very. In synchronous machine, synchronous reactance is much more. Okay. RA drop, RA can be neglected many times.
And the XA value ఉంది కదా సార్. XA value may exist, sir. ఉండొచ్చు ఉండకపోవచ్చు.
That is fictitious, no? Imaginary. We are modeling. It is causes drop. How drop you can explain? How you can model?
Sir.
Drop in a resistance or drop in a reactance. That's all.
Yes, sir.
That's the reason we are representing in a reactance.
Even the unity power factor IA will exist, sir. XA value.
Exists. Yes, yes. It is cross magnetizing. Resultant will exist.
Sir, ZPF lag diagram once open.
And even for normally, for example, what is that?
ZPF lag diagram, sir.
Armature reaction.
Yes, sir. Physical diagram, sir. Physical diagram.
This one.
Yes, sir. Sir, I did not understand right side diagram, sir, because what is the main flux? What is the armature flux?
Main flux and rotor flux. North pole is there. Here North pole. This is giving the flux. North pole flux is coming out. North pole నుంచి బయటికి వచ్చే ఫ్లక్స్ అదే మెయిన్ ఫీల్డ్ ఫ్లక్స్. అయితే ఆ ఫ్లక్స్ రోటర్ మిషన్ బయటికి వెళ్ళి రావట్లేదు, ఎయిర్ గ్యాప్ లోనే ద ఎయిర్ గ్యాప్, బట్ ఐఎమ్ ఎక్స్టెండింగ్ దట్ ఫేజర్ phi.
Armature flux, sir.
Armature flux. Apply thumb rule. This is cross kada, ఇది cross. E cross same ఎప్పుడు, always the maximum value of E will be under north pole, under south pole only.
Okay, sir.
Okay. Rotor is rotating in counterclockwise direction. That's the reason I am saying this is cross, this is dot. Okay. Now you E maximum here. But where current maximum, tell me? Rotor is rotating in counterclockwise. 90 degrees lag కావాలి. IA maximum must lags the E maximum by 90 degrees. అంటే ఎక్కడ రావాలి? It should be here. Correct? Here crosser.
Sir.
Similarly, dot is there. Dot of the current also should lags the dot of the voltage by 90 degrees. This is dot. This dot, 90 degrees. You compare.
So red color the armature flux, blue color the.
మరి అదే కదా, రెడ్ కలర్ ఆర్మేచర్ ఫ్లక్స్.
Okay, sir. Understood.
థంబ్ రూల్, ఎంటరింగ్ లీడింగ్. అదే లీడింగ్ అనుకోండి. లీడింగ్ అంటే ఎక్కడ వస్తుంది చెప్పండి? లీడింగ్ క్రాస్ విల్ కమ్ టు హియర్. దిస్
dot will bottom side.
Then flux will be in same direction of main field flux. Both will be aiding. Okay.
Okay, sir.
Right. Next, hello.
Thank you, sir.
Hello, tell me. Hello. Yeah.
Sir, excuse me, sir. Sir, ఇక్కడ ఆల్టర్నేటర్ కి సింక్రోనస్ మోటార్ కి డిఫరెన్స్ వస్తుంది కదా సార్. ఇక్కడ ZPF ఫ్లాగ్ లో ఇక్కడ డిమాగ్నెటైజేషన్ అయితే అందులో మాగ్నెటైజ్ అవుతుంది కదా సార్. అది డిఫరెన్స్ ఎలా వచ్చింది ఒకసారి చెప్పరా సార్?
కరెంట్ రివర్స్ అవుతుంది.
ఓకే, ఫేజర్ డయాగ్రామ్ లో చూపించినట్టు సార్.
ఫేజర్ డయాగ్రామ్ లో ఇక్కడ చూపించాను
సార్. ఓకే సార్.
కరెంట్ ఆపోజిట్ కాబట్టి ఆర్మేచర్ రియాక్షన్ ఎప్పుడు ఆపోజిట్ ఉంటుంది దానికి. ఇది
ఓకే సార్. థ్యాంక్ యూ సార్.
Okay, right. Next. Hello. I'm unmuting.
Hello, sir.
Hello.
Hello.
Hello. Tell me.
Sir, in the diagram you've taken both motor and generator. That phasor diagram. Here, sir. Here, how can we refer so that V will be opposite to that generator, but E is same. Yes, it is 90 degree lagging.
Motor, this is EB, na? EB here. Back EMF here. When you are decided EB here, where should be V? Phase opposition. Because why it is called back EMF? E and V both will be in phase opposition. Generator E and V same direction. E and V opposite direction. In motor, back EMF.
Okay. And
sir, V I am writing.
When
V, IA should lags.
Lags. Okay.
Here also blue color of IA lags, blue color E. Generator voltage, generator current lagging, and power factor is angle between V and IA.
Okay. Sir, and when we are drawing the phasor diagram of that when in the motor case, in the leading case, we will get that E value is more than V.
Where?
In motor.
In motor, which power factor?
Leading power factor.
Yes, yes, E will be more.
Then
EB,
you said a point that you asked a point that this is due to that delta lags is due to the drop.
Yes, yes.
But
Drop or
how
rise it
that
may be.
drop
Drop or
magnitude
rise.
changes?
IA ZS may be drop or rise, both. IA ZS, that's all. It may be drop or rise.
Okay.
General
And
case, I am taking
here
drop. General case, I am taking drop. Normally, which power factor takes place? Lagging, no? Lagging. Lagging power factor, it will be drop.
and okay, sir. Okay.
If you want, you can write IA ZS drop in bracket rise. You can draw. Right.
And
Drop
you
or rise.
also said a point that that drop will be capacitive in nature also. Can be.
Yes, yes.
Can be.
Yeah, XCA maybe even XCL you can take, XCC also you can take.
But we never in any book or I seen that that drop is always a reactance drop. That will be a motor or generator.
Why? Because it is inductive nature. Loads are inductive nature, na? Loads
But
are inductive nature.
when is the case when capacitive will be come into picture? That XA.
Yes, yes. That is very rare. Capacitive loads where you will use practically. Never.
Okay.
No capacitive loads. Mostly inductive loads. Capacitive very rare. Okay.
Okay.
All right. Next. Hello.
Thank you, sir.
Thank you. Anyone? Hello. Yeah. Tell me, ma. Who is there? Hello. Hello. Anyone is there?
Once explain about EB, sir, back EMF, how it is in that direction.
EG and EB is a synchronous machine. Flux direction is fixed along D axis. No? Flux direction is phi m along D axis. Flux is along the D axis. See, flux is along D axis. Induced EMF always along Q axis. It may be generator or motor, whatever it may be. This lags 90 degrees. This is fixed. Motor or generator, EG or EB. Equations are same, na? EG and EB is equal to 4.44 Kp Kd phi ft. Induced EMF lags the flux by 90 degrees. That is fixed. Okay, this is EG, this is EB. Fine. Now, for generator E, V also in same direction. I am drawing for lagging power factor. This is current. Okay, lagging. But for motor, what is the current? EB means V will be this side. For lagging power factor, IA should lags. This is IA. IA lags this V. This is the power factor angle. Now, same both for 0.8 lagging only. IA and IA for generator motor opposite direction.
Yes, sir.
EB is induced EMF. In motor, back EMF you can find by applying right hand rule or left hand rule. Right hand rule.
Right hand rule, sir.
Induced EMF always right. It is induced EMF. That's all.
Yes.
Generator or motor, for generator you will rotate. It cut the flux. Motor it will rotate. It also cut. Okay.
Okay, sir.
Fine.
Hello, sir. Am I audible?
Yeah, audible.
Sir, slide number 11.
Slide number 11.
Sir, your rotor is moving in counterclockwise direction, so south pole is moving up.
Exactly.
But I'm not getting that Emax cross, sir. How is that cross?
Pole is moving. When conductor is stationary, what you have to do, ma? You have to assume in downwards.
Okay,
I
sir.
have given conditions, na? Very
Yes.
beginning classes.
Yes,
When
sir.
conductor is stationary, you have to assume opposite direction of field rotation. So
Okay,
pole moving
okay, sir.
upwards, conductor you have to assume downwards cross.
Okay, sir.
Yeah.
Got it, sir. Thank you.
Okay. Hello, next. I'm unmuting all the students.
Hello,
Hello.
sir. Can you explain this angle between main field and MMF field terminal voltage? Sir? No, sir.
Terminal voltage, how much? You see the from phasor diagram. Phasor diagram, no?
Yes, sir.
Where is it?
Sir.
Here.
See,
See, phi m to E, how much angle? 90.
90, sir.
90. E ki weak ఎంత angle? Delta.
Done.
90 plus delta.
Okay.
Okay.
So, okay. Sir, can you explain equivalent alternators? Equivalent circuit of alternator. I can't understand.
Equivalent circuit. This is equivalent
Yes, sir.
circuit. Oh,
Yes, sir.
E is there. E minus IAXA. That is ER.
Okay.
Air gap voltage ante E లో నుంచి armature reaction drop, because E 450, ER 430.
Okay.
That is armature reaction drop. And after that, you again subtract XL drop, RA drop, then you will get B.
Okay, sir. Thank you, sir.
Right. Yeah. So now I am closing the session. So we are going to see tomorrow the other topic.